Today's lecture is about resistance, resistivity, and Ohm's law. Moving on in our little series about currents, this is in chapter 22. Hopefully you got signed up for the online book. If you didn't see those resources, they're in Google Classroom. I'm going to start doing homework through the textbook portal because it's way easier for me and it's the same questions for you guys. So check for it there. If you're not signed up, please go see the stuff in Google Classroom and get signed up. If you're having technical difficulties or you need some help, let me know. I'll try to fix it for you. Before we get into the resistance and resistivity and Ohm's law, we first need to talk a wee little tiny bit about potential and current. They're the things we've already been going over it. But the rule that we haven't talked about yet is that the potential difference across a battery has to be the same as the potential difference across the wire. And there's pictures here, I'll explain in a minute, but here's what this looks like in circuit form. So you'd have a circuit with a battery, looks like this, and you have a certain voltage across the battery. That's a rating of the battery. Say it's a 9-volt battery, very common voltage for a battery. If that potential difference is measured at 2 points right on either side of the battery, that means that the potential difference between those 2 points across the battery is 9 volts, but also the potential difference around the circuit at those 2 points is 9 volts. So somewhere along the way between those 2 points, as charge flows around with potential energy, it has to lose potential energy according to a 9-volt potential difference. So all of that energy gets dissipated somewhere in the circuit along the way, so that the difference between the terminals is the same as the potential difference across the entire circuit. And the reason why these pictures are relevant here is basically, sorry, my circuit's not moving. Let's move the circuit out of here. Basically, this means that as the charge goes up in potential energy, which is what the battery does, it has to come all the way down the slide to the bottom in order to get back on the ladder and go up. If it doesn't come all the way down to the bottom, it doesn't meet up with the ladder, so it doesn't work, and the circuit will just not operate. And then these things over here are called the Penrose stairs. They're a mathematical and optical illusion. If you follow the Penrose stairs here, you see that as you go up the stairs, you'd say the stairs are like the battery. If you didn't go down when you went through the circuit, you'd end up back at the battery where you keep getting lifted up. So energy would keep being added to the circuit without ever being lost, which sounds something like infinite energy, which is not a reality, unfortunately, in our world. So in order for anything to make sense, all of the energy gained in the battery has to be dissipated over the circuit, so the potential difference across the battery is going to be the same as the potential difference across the wire. Also, I just played back that audio and realized my dryer is going in the background, so sorry for the background noise. Not going to re-record all that. Okay, moving into today's real topic, resistance. For any wire, we define a quantity called resistance. That is a measure of how hard it is to push charges through the wire. And mathematically, it's easier to define mathematically. It looks like resistance equals voltage in a wire divided by R, which looks suspiciously like a rearrangement of Ohm's law, because it is. But it essentially defines resistance as the amount of potential difference across the wire for a certain amount of current, and that's related to the potential energy that is dissipated inside the wire for a certain amount of current. And this is measured in ohms, because Ohm is the guy that really worked with resistance. 1 ohm is 1 volt per amp, as you could see from the lovely equation. And ohm is represented by this capital omega. Resistivity is our next vocabulary thing, and it is different from resistance. Resistance is a property of a specific component of a circuit or a specific wire, like a piece you could physically hold and see. And you could say, this is the wire, it has a certain resistance. And it's based on properties of that wire, like the length, the gauge, which is the thickness of the wire, what it's made of, and its temperature, and other things possibly. Resistivity, on the other hand, is a property of a material, and it doesn't change within a material. So all copper has the same resistivity. All nickel has the same resistivity. It's just a property of a material. You could go Google resistivity of iron or resistivity of cobalt, and it would just be some value for that material. You don't hear it because I keep deleting it, but I have been unable to say the word resistivity about 6 times in a row now. Anyway, good conductors have low resistivity and bad conductors have high resistivity, which makes sense because you would expect something that conducts electricity not to resist that conduction a whole lot. And something that doesn't conduct would have a high resistivity because it does resist the flow of electricity a lot. Resistivity is related to resistance by this equation here. So the resistance of some component, or of a wire in this case, is resistivity, which is this Greek letter rho, times the length of the wire divided by the cross-sectional area. I assume we know how to take a cross-section, but I'm going to draw it here for you. Like if you have a wire that looks like this, it's round. A cross-section is going to be a circle slice of that wire. So that cross-sectional area is the A here. If you work out and rearrange all of the units for this equation, you'll see that resistivity, which is that rho, is ohms times meters. So again here to reiterate, the difference between the two is that resistance is a property of a specific wire or component, whereas resistivity is a property of a general material like copper or nickel, whatever the thing is made of. In real life, this is what some resistors look like. If you take a circuits class ever, you'll probably get a breadboard and a bunch of these little resistors. They are rated to have specific resistances, and those specific resistances are indicated by these colored stripes. You can look up charts for resistors that'll tell you what the pattern of stripes means. So something that has 3 red stripes and a gold stripe will have some amount of resistance. It's all in some electrical chart somewhere. This is what they look like in real life. Resistors are used to control current and voltage in circuits, which is really useful for when you need to route signals through some electronic device. You can use resistors to take that current, which is where the signal is found. And resistors are also used to take the electrical energy that's flowing through a circuit and transform it into something useful, because electrical energy all by itself is pointless. It could just shock somebody. All you need to do is transform that electrical energy into something that does what you want it to do. And what we're going to start doing with resistance is using it to calculate a current for specific potential differences, or to calculate potential difference given a specific current, all the things for circuits that you may have done before. So this is Ohm's law, V equals IR. It looks very similar to the previous equation for resistance, which was resistance equals V over I. That's because there's the same equation. Algebraically, they are equivalent. Now, Ohm's law is going to be good for this class, but in reality, it is not one of those laws that's like always true. Now, there's some laws that are always true. That, as far as we know, this is not one of them. Ohm's law only applies when resistance is constant, but in reality, resistance is usually not constant. It changes mostly with temperature. So if you can imagine a wire made of atoms, sorry, that's poorly drawn wire. The wire is made of atoms, and as current runs through it, it runs into the atoms, which makes the atoms jiggle. Atoms jiggling is what temperature is. So the more the atoms jiggle, the higher the temperature is. So as current goes through a wire, it raises the temperature. Now the jiggling atoms are more likely to impede the progress of the electrons that are trying to move. So as temperature goes up, resistance also goes up. So Ohm's law doesn't exactly apply with that temperature change because resistance is changing as current flows and the circuit heats up. So Ohm's law is not always true. And there's some materials that are more, quote, ohmic than others. Some are non-ohmic. A material is ohmic if Ohm's law is true for that material and current and voltage are linearly related by the proportion R, or resistance. So Ohm's law is not always true. Some major examples of this are superconductors. Superconductors operate at super low temperatures, like 4 Kelvin. They're cooled by liquid helium. And temperature variations in superconductors change them drastically. It's crazy. So if you have a superconductor operating at 4 Kelvin and it heats up over a threshold temperature that's not that much higher than 4 Kelvin, it becomes an instant insulator and it will conduct no current, and it destroys the superconductor and it destroys whatever component it's in. It's crazy. I actually worked in a lab designing superconducting magnets, and this was a huge worry, was that if something happened and the magnet heated up a little tiny bit, the whole thing would be destroyed. So it's a very big deal in the worlds of industry and like actual physics and engineering that Ohm's law is not true at certain temperatures for certain materials. In the scope of this class, we're going to say it's true, but I always like to point out where the little discrepancies in real world cracks would break through. Sorry about that aside. I just really like superconductors and they're really cool. Come talk to me about them sometime if you want to know more. All right, now we get into the fun part of the lecture, which is the assumptions that we make when working with simple circuits. So one of the assumptions is that Ohm's law holds true. Another thing that we're going to assume is that we are using ideal wires. Ideal wires have no resistance, so there's going to be no energy loss inside the wire. But this doesn't really make sense from a physical standpoint. Because if there's no energy loss in a wire, that means there's no potential difference across that wire, because the charge is not changing potential energy, so there's no change in potential in that wire, which means there cannot be an electric field there, which means there cannot be any current, because the field is what's going to drive the current. So technically, if you have a wire with no resistance, you're not going to have a potential difference, which means you're not going to have any of these things. It's really weird. And the truth of the matter is that if you had no resistance, the circuit just would not flow, because there would not be a potential difference for it to flow through. Which is going to take us back to these Penrose stairs, where if you started and went through the battery, got up to some potential, didn't lose any energy, got back to the battery, you just keep ramping up the energy and ramping up the energy forever and ever and ever, well, until your battery runs out anyways, which would just be crazy and is not how circuits work. So ideal wires are kind of problematic in that aspect. Side note, here's a couple more Penrose stairs things that I like to look at. This one's a pretty cool graphical representation. It's really started out as the Penrose triangle. But yeah, just an infinite loop, always moving upwards. Really weird optical illusion. And, of course, if you're a Star Wars nerd like me, here is my favorite meme, probably my favorite meme of all time. There's one other meme that might rival it, but this is probably my favorite meme of all time. It's the Penrose stairs with Anakin and Obi-Wan. Some lovely quotes. If you want to go look at the slides, click on that link. There's a nice Reddit where this was posted, and it has a great thread if you want to read through that. Just for your personal enjoyment. I personally enjoy it. It's very much not related to what we're doing, but just thought it might brighten your day. So to deal with this assumption of ideal wires, we're going to say that the resistance is close enough to zero that we're not going to calculate it, but it's far enough away from zero that we don't have to deal with the consequences of an ideal wire. Another assumption we're going to make is that resistance is kind of linear in a resistor, so that the potential difference somewhere inside the resistor is linearly proportional to the voltage across the whole resistor. So for example, if we said that dot is halfway between the two terminals here. I know it's not, but I'm not drawing things to scale. If we said that dot was halfway across and the whole resistor had a potential difference across it of 2 volts, halfway in the middle would be half of that potential difference. So that would be 1 volt. It's just linearly related. That's the assumption we're going to make. All right, real quick, we're just going to look at a single resistor circuit. A couple of things about it. I'm going to draw it over here. We've got a 15 ohm resistor connected to the terminals of a 1.5 volt battery. So this is going to be my battery. There's my positive end. There's my negative end. Circuit goes around, has a resistor. That is the universal circuitry sign for resistor, basically a squiggly line. Goes around to the negative terminal over there. And what the question asks us to do is, starting from the negative terminal, where we're going to put V equals 0. Starting there, if we move around the circuit, what the potential looks like. We're going to graph that. Let's see, let me fill in my values here. This is 15 ohms, and this is 1.5 volts. So if we draw this on a graph, starting at the negative terminal, as we go from the negative to the positive terminal, the charge is gaining energy, it's gaining potential. So it goes up like this. It's like riding the escalator up the thing that was talked about in the other video. So after it gets to the positive terminal, which is going to be right here, it's going out on the wire. And along the wire, we're saying there is no potential difference. There is no change in potential. So we're not losing any energy. It's just flatlining. Sorry, that's not a very flat looking line. Until we get to the resistor. And then at the resistor, we linearly lose potential across the resistor. So this is going to be a start of resistor to the end of the resistor. And you notice it goes all the way to the bottom because we can't lose any potential over the rest of the wire because it's an ideal wire, quote unquote. And it's 0 again at the negative terminal. So we end up down at 0, flatlining out again. So the graph of the potential would look like that. The other question is, what is the current of the circuit? This is just Ohm's law. V equals IR. So I equals V over R. Current is what we're looking for. Voltage is 1.5 volts and resistance is 15 ohms. So our current there is 1.5 divided by 15, which is simply 0.1. And volts divided by ohms is the correct unit for current, which is amps, 0.1 amps. All right, this should get you through a fair amount of the homework. The homework is currently in 2 parts. One part is the one I typed up and is in Google Classroom. The other part is in your Pearson Mastering Physics Lab, whatever I put for the virtual book or the online book information. There's a homework assignment through that portal. If you have trouble accessing it, let me know and I'll try to get you some help, but you can complete it in there. It doesn't take off points for wrong attempts on answers, but it will tell you if your answer is right and wrong. It'll give you multiple attempts, and it will sometimes give you feedback to help you figure out what you're doing wrong. As always, let me know if you have any questions. Show up to office hours if you need help. Honestly, I have forgotten to show up to office hours myself the past 2 days because I was so busy I forgot they were even supposed to be happening. If you show up to office hours and I'm not there, please email me and I'll hop on whenever you need. All right. Hope y'all have a great day and let me know if you got any questions.